So in this video we're going to keep discussing Philip-Hall's theorem, and we're going to prove the other direction of the Philip-Hall theorem. But first we have to prove some lemmas, and these are both homework exercises from section 3.3. The first lemma is that if you let P be a CeLO subgroup of G, and you let N be a normal subgroup of G, then P intersect N is in fact a CeLO subgroup of N, and Pn mod N is a CeLO P subgroup of G mod N. Alright, let's do some setup here. First we're going to write the order of G as P to the N times M, where the GCD of N and M is 1. And the order of N, the normal subgroup, is P to the K times D, where the GCD of K and D is 1. We're going to work on the first claim first. So how are we going to do it? Well, let Q be a CeLO P subgroup of N. Well, then Q is a subgroup of N, which is also a subgroup of G. So Q is a P group in G. By one of the CeLO theorems, every P group has to be contained in a CeLO P group. So in particular, there exists a CeLO P group of G with Q as a subgroup. Of course, the way that second CeLO theorem was stated was that you might have to conjugate Q, or equivalently, you might have to conjugate P. So you might remember the original statement was you were given P and Q, and the point was that there existed a G, such that GQ G inverse was a subgroup of P. But here we're working the opposite direction. Since CeLO P subgroups exists, and the conjugate of a CeLO P subgroup is a CeLO P subgroup, just redefine P to be this conjugate. We move this over, and then we just redefine P to be this new one. And congratulations, you have a CeLO P subgroup containing Q. Alright, so then what happens when I intersect P with N? Well, I get a subgroup of N. And because the way this intersection works, Q intersect N is also a subgroup here. Oh wait, but that's already Q, because Q is a subgroup of N already. So we see that Q is a subgroup of this intersection. But remember, Q was a CeLO P subgroup of N, and so Q had to be a maximal P group. And P intersect N is a P group. So that implies that P intersect N is contained in Q, which means that Q is P intersect N, which means that P intersect N is in fact a CeLO P subgroup. So there's a way to use the CeLO theorems to get this proof direct using other theorems instead of using counting arguments. And so we see that P intersecting a CeLO subgroup with a normal subgroup gives you a CeLO subgroup inside the normal subgroup. Now what about this quotient business? Well, that one's a little easier to prove, because now I'm going to actually look at the size considerations and recognize that by one of the isomorphism theorems, this is isomorphic to P modulo P intersect N. And so the order of this group is P to the N minus K. On the other hand, the order of G mod N is seen to be to P to the N minus K times M over D. And so the size of a CeLO P subgroup in G mod N is P to the N minus K. And we have a group of that size. So Pn mod N must be a CeLO P subgroup in the quotient. All right, the next lemma concerns Hall subgroups. Let H be a Hall subgroup of G. And let N be a normal subgroup of G. Then H intersect N is a Hall subgroup of N. And similarly, Hn mod N is a Hall subgroup of G mod N. So what do you have to do in order to prove this? Well, what are you checking? You want to check that the GCD of H intersect N in N, and the size of H intersect N is 1. That's what we want. What do we know so far? That the GCD of the index of H and G and the size of H is 1. Note what this implies, that if you write G as a product of its prime powers, then for each prime power, you're either going to have Pi to the Ai divides the order of H, or it divides the index, but not both. Why is this true? Because, well, if you ever had a smaller power that prime divide the order of H, well then you already know that the order of G is actually factors as the size of H times this index. And so you would see, for instance, if you had a smaller power dividing H, then the leftover power would have to divide the index. And then there would actually be a common factor, which is a contradiction. So this is a fact we're going to use. So here's what we're going to do. We're going to take a prime dividing the order of this intersection. Now we're going to take the smallest k with p to the k dividing the order of the intersection, but p to the k plus 1 does not. And what do we need to show? We need to show p does not divide this index. If that is true, then the prime power factors here None of those primes are over here, so they have no prime factors in common at all, so the GCD has to be 1. All right then. So what are we actually going to do? We're going to take a CeLO P subgroup of H. We're going to apply the previous lemma and conclude that P intersect N is a CeLO P subgroup of H intersect N. Although here I should be a bit more careful. What do we actually know is, based on size considerations, it's also a CeLO subgroup of G, and then by the previous lemma, that implies that P intersect N is a CeLO P subgroup of N. And of course, because P is a subgroup of H, it follows that P intersect N is a subgroup of H intersect N. And so you have a subgroup of H intersect N of the highest prime power order in N that is possible. So that's enough to tell you that the index can't be divisible by a prime. That is, based on subgroup conditions, this index is equal to a ratio of indexes all the prime powers are taken care of in this group. So this numerator does not have any power of P in it. And so this doesn't have any power of P either. And so we finally managed to show what we wanted. For any prime power, any prime divisor of H intersect N, that prime does not divide the index. And so these two things are relatively prime. Therefore, H intersect N is in fact a Hall subgroup. So that takes care of this part. Similar argument's going to work for Hn mod n. The only part that's different is that instead of working with P intersect n, you'd be working with Pn mod n. It's a CeLO P subgroup of G mod n, and is also clearly a subgroup of Hn mod n. And then you could do the same type of index calculations we just did, and you'd be able to conclude that there are no prime divisors of the corresponding index. So you'd be able to prove that the GCD of G mod n and Hn mod n and the order of Hn mod n also end up being relatively prime.